Good morning, everybody. I'm Serena Giardiello. I'm a postdoc at Cardiff University, and I'm going to give a general overview on the Simons Observatory experiment, its science goals, and a brief description of the telescope. So the ESO collaboration is a pretty big collaboration. It has more than 300 collaborators spread over more than 40 institutions. You can see all of them at the bottom of the panel, and they are spread over 10 countries. This is a picture from the last face-to-face meeting in San Diego. Unfortunately, we didn't have one this year because of the commissioning of the telescopes on the site. This collaboration is funded privately by the Simons and Ising-Simons Foundations. Even though at the end of the talk, I will mention opportunities given by public fundings and how they will expand the current project. So ESO is a ground-based next-generation CMB experiment. It is expected to provide breakthrough discoveries in cosmology, particle physics, and astrophysics as well. As I was saying, it is now being deployed in the Atacama Desert, and the first data are expected in 2024, so next year, early next year. A brief recap of the main observable, which is the CMB radiation. It has been generated around 300,000 years after the Big Bang by the Thomson scattering of photons and electrons, and after the recombination of electrons and protons into hydrogen atoms, the CMB photons were leaving the last scattering surface and traveling the universe. And what we observe today are photons that have crossed a whole phase of all the phases of evolution of the universe. So, for example, phase of reionization, where the CMB photons have been reionized by the first stars, all the formation and evolution of structures that, for example, have bent the path of the CMB photons through weak gravitational lensing. Another effect that we observe is the Sunyaev-Zeldovich effect, which is the inverse Compton scattering of the CMB photons off to the higher energy electrons that are present in the galaxy cluster and allow us to trace them. Then the CMB is sensible also to the particle content of the universe, the presence of neutrinos or relativistic particles. And on top of that, as we have already mentioned, we have foreground signals coming from both our own galaxy, from dust and synchrotron emission, and also extragalactic sources that we can observe, like high redshift dusty galaxies or radio sources. And we have to be aware of all these contaminants. Okay, this is a schematic overview of the main science goals of ESO. Like other next generation CMB experiments, it will track the observation of primordial B modes generated by a primordial gravitational wave background sourced during inflation. So high sensitivity detection, observation at least of primordial B modes. And so the goal is constraining the tensor to scalar ratio with lower sensitivities than currently available. Then also constraining an effective, so the effective number of relativistic degrees of freedom, which parameterize the relativistic species in the universe, the reionization phase through the Sunyaev-Zeldovich effect, the neutrino mass, as we were mentioning also this morning, neutrino mass affect the matter power spectrum and the matter distributions, and so we can constrain that through tracers of the matter distribution, like gravitational lensing, Sunyaev-Zeldovich effect, and also, of course, large-scale structure surveys, which are external to ESO. ESO can give information on galaxy evolution parameters, on dark energy by constraining sigma 8 and H0. And finally, since we have to study our foreground signal, for example, from our own galaxy, we will advance also in galactic science, for example, knowing about galactic magnetic fields, or we can also look for local objects like Planet 9 or other local objects. So SO is made up of two kinds of telescopes. The small aperture telescopes, in the baseline configuration, we will have 3 of them, the SATs. It's basically a telescope designed to achieve one specific goal, which is the observation of B modes with high sensitivity. To do that, they will be equipped with rapidly spinning half-wave plates like other next generation experiments that will target B modes like Lightbird. This will reduce sources of noise and systematic effects, while all the other goals are covered by the LAT, which is the Large Aperture Telescope that will have a high angular resolution. So it will observe and track the small angular scales that are fundamental to achieve all these science goals. Okay, this is a look of the power spectra expected for SO, which are the blue dots here in the TT, EE, and BB power spectrum. So as I was mentioning, the LAT will reach a very high angular resolution. So it will arrive up to L9000 here in the TT power spectrum. The plot is cut here because at very high L multiple, the CMB signal becomes very faint, and the foreground signal becomes instead very relevant. So it has to be taken into account in the analysis. Then regarding the B mode power spectrum, which will be observed by the SAT, the lower multiple will be L30. So as we were already saying before, to constrain R, so the tensor to scalar ratio, it is important to observe these bumps, the reionization and recombination bump. We cannot really access to the reionization bump because it is a very low L multiples and it can be observed only from space. We are limited by atmospheric contamination, and so we will track the recombination bump, and then at much higher multiples, we are very dominated by the lensing signal. But since the LAT will have a very high angular resolution, it will observe the lensing signal, which will be used to de-lens the BB power spectrum observed by the SATs. And then looking at the intermediate and small angular scales in temperature and polarization, we will learn about an effective which affects the damping tail of the CMB power spectrum, or also neutrinos which affect the acoustic peaks, or other exotic particles which affect them as well. And all of them can be, of course, constrained also by the lensing spectrum, which is not shown here. Okay, this was just to give a general overview of some of the forecasts that have been done for the SAT and the LAT. This comes from the last SO forecast paper from 2019. So here we have the R and S plane. So concerning the SAT, the gray contour comes from the most recent data sets, like the most stringent constraints that we have from previous and current data sets. In orange, we have the constraints expected for the SO nominal configuration. So SO is expected to reach a sensitivity on R of approximately 3 times 10 to the minus 3 in the nominal configuration, and for a model with R equal to 0. The red contour refers to a configuration which has a slightly lower noise level. Instead, in blue, we have all forecasts that refer to small-scale science. For example, constraints on the sum of neutrino masses. SO is expected to achieve a sigma on the sum of neutrino masses of 0.04 electron volts by combining CMB lensing and the larger scale structure surveys, or constraints on an effective, which is expected to have a sigma of approximately 0.07. From the astrophysical side, constraints on galaxy evolution parameters. We will have also, this is a prediction of the observed the Suniev-Zeldovich cluster for different redshift. So SO is expected to leave a legacy catalog of approximately 20,000 Suniev-Zeldovich clusters. And another example is constraints on the fraction of dark matter made up of ultralight axions. So, of course, these are not all the key forecasts on the key science goals because they would not fit in just one slide. And if you are interested in these forecasts, you can find them in the same paper from 2019. You have complete tables with the key forecasts on the key science goals and additional goals that I've not mentioned, like constraints on primordial non-Gaussianity, Big Bang nucleosynthesis, and the nature of dark matter and dark energy, and also all the expected legacy catalogs by SO. Another contribution will be given in millimeter transient science. So since the LAT will scan several times the same patch of the sky with very high angular resolution, we will be able to observe clusters through Suniev-Zeldovich effect, high redshift dusty galaxies, radio sources, but also we can observe transients like variable AGN or possibly afterglows of gamma ray bursts. So it will be important to set up a system of transient alerts to communicate with other collaborations. Okay, just a final overview of all the fields to which SO will contribute, from cosmology, particle physics, to extragalactic astronomy with all the legacy catalogs, to galactic astronomy, since we will study foreground signal from our own galaxy, variable sources and local objects. And last but not least, also training the next generation of scientists, since it's a quite big collaboration made up like other collaborations by early career scientists. And SO is also committed to outreach. There are many outreach activities, especially based in the US, since it's a US collaboration. I wanted to highlight this mentorship program, which is a very nice program in which more advanced career mentors meet regularly with one mentee, which is more early career, and they discuss about anything which is not strictly science related. And I think it's a great program, which also creates a connection between different generations of scientists. Okay, let's now discuss about the site. So SO is built in the Atacama Desert in northern Chile. The site is at 5,200 meters of altitude. It's a very dry site, which is important not to have contamination from water vapor. And it's a very well-established site since we have already Simons array class and duct. But there is still some room for expansion for the SO nominal site, as we will see later. So we have 1 LAT and 3 SATs, as we were mentioning before. We have also those very nice pictures from the site, from people that is working there in these last months to deploy the telescopes. So, for example, the LAT receiver has been mounted on the LAT like a month ago. Now they are deploying the SAT receivers. And they are sending us lots of beautiful pictures of the LAT, the SATs, and the sites like these ones. Okay. So a closer look at the LAT and the SAT. So the LAT is a 6-meter telescope. It has only 7 optics tubes in the nominal configuration. These tubes are dichroic, so they have arrays that observe 2 frequency channels. The frequency range is from 2739 to 220, 280 gigahertz. And we have more tubes, of course, in the middle frequency channels that, as we have seen before, are the most important channels for the observation of CMB because they are the least contaminated by foreground signal. In total, the LAT has approximately 30,000 detectors, like the sum of all the SATs. The SAT are half-meter detectors, and they have 4 receivers, basically in the same frequency channels, and more receivers in the middle frequency channels. And both the LAT and the SATs have transition edge detectors. Okay, about the survey, the SAT survey is like optimized and targets the B mode observation. So the SAT will observe a pretty small fraction of the sky, so only 10% of the sky. This region excludes the galactic plane in order to reduce foreground contamination, which is is very relevant for such a faint signal like the primordial B mode signal. It also has a limited range of elevation in order to reduce atmospheric noise. The resolution is half a degree at 93 gigahertz, and the noise level is pretty low, so 2 microkelvin arc-minutes co-added over the middle frequency channels. While the SAT will observe a larger fraction of the sky, approximately 40%, and this patch of the sky is optimized to overlap with DAISY and LSST, so larger scale structure surveys, which is important for cross-correlation with these surveys. The resolution is much higher, so we have arc-minute resolution in the middle frequency channels, and a noise level of 6.5 microkelvin arc-minutes co-added over these channels. So the first big news that I was mentioning before is that through public fundings from UK and Japan, 3 more SATs will be added to the current configuration. So we will have 2 more SATs from the SO UK project and 1 more SAT from the SO Japan project. So with this addition, we will go up to 90,000 detectors and have, in general, twice a better sensitivity on B modes, since we will have twice the SATs. And I wanted to describe a bit also the SO UK project, since I'm a part of it. So it started in October 2020. It does not just include the addition of 2 SATs, but also of 1 more LAT optics tube at ultra high frequency. Contrary to the American counterparts, which have TES detectors, these SO UK detectors will be KIDS, so kinetic inductance detectors, because the UK, in particular Cardiff, has a lot of expertise on these detectors. Plus, the SO UK project includes the setting up a data center in Manchester, which will store the science-ready data products, which will be the maps for high-L science, for B modes, or for lensing that are ready to be analyzed to extract science from them. And of course, these products will be available to the whole SO collaboration, not just to SO UK members. And also setting up algorithms and pipeline that are important to arrive to these science-ready data products. Okay, second big news is that the Advanced SO project has been funded by the NSF, so by US fundings. This will include 6 more LAT optics tubes. So in total, with the nominal configuration plus those 6 optics tubes plus the SO UK one, the LAT will have double the optics tubes at the end. Setting up also a data management program in which the full maps will be processed in 6 months, and a daily transient alerts will be set up. And very importantly, the addition of a photovoltaic array on the site. This will reduce the carbon footprint by approximately 70%, which is very important for our collaboration, since we are very aware of our environmental impact. And the Advanced SO operation will run from 2028 on. I forgot to mention that the 2 SATs will be commissioned around 2025-2026, while the SO UK LAT optics tube will be commissioned in 2026. So for timelines, advanced SO will start on 2028. And I remind you, the SO project observation will start next year. So I will stop here. I guess you are all, like me, thrilled by the fact that we will have the first SO data next year. And thanks you all for your attention with this other beautiful picture from the site. So thank you.